along with this standard reduction potential. So here is an example. I'm going to walk us through on how we calculate our standard cell potentials from the standard reduction potentials. Okay, so just to point out here, right, we've got the same example that we've seen before, where we have a zinc anode and a copper cathode, and this combination of half cells gives us a voltaic cell. So it's a spontaneous reaction. It gives us some juice that we could charge our cell phone with, for example. And this, as we can see right here, would be our standard cell potential, which is the combination of both half reactions, right? So that's what we would measure out of this voltaic cell, 1.104 volts. So how do we get that? Well, we have this equation, E cathode minus E anode. And here I've got both the copper and zinc reactions written as reductions, right? And so you can see the zinc reaction has a negative cell potential, whereas the copper has a positive cell potential. And it might not be straightforward yet, but we want to see typically the most negative cell potential as the anode for the following reason. So cells are arranged in a way that maximizes the cell potential to be positive. We'll see why that is soon, okay? And so if we were given that choice, if we were saying, okay, here's some copper, the copper reduction reaction, here's the zinc reduction reaction, which one do you want to choose as the cathode and anode? We would choose the most negative one as the anode because when this reaction, the calculation, right, is E cathode minus E anode, both as reductions, you can see what happens is 0.342 volts minus 0.762 volts. So that double negative becomes a positive, and we get that 1.104 volts, which is what we would measure in this voltaic cell. Okay, so now that's pretty advanced, just looking at this and kind of knowing which one we should pick as the cathode and which one we should pick as the anode. So if it wasn't clear on how to do that, then we could attempt to balance these reactions like we've done in Chem 109, okay? And also noting that, right, we want E cell to be positive. That's always our goal, is to arrange this so it's positive. So if I was writing this down, I'd recognize that if I flipped the copper reaction, I'd have a negative plus a negative, which gives me a negative. But if I flipped the zinc reaction, it would become a positive, and a positive plus a positive gives me a positive. So that means I would want to keep the copper reaction written as a reduction, okay? And so that's still 0.342 volts. And because I'm keeping it as a reduction, remember it has to be at the cathode, okay? So our reduction half is always at the cathode in a voltaic cell. And now I want to flip this reaction to cancel the electrons, right? So that's going to go zinc solid becomes zinc 2 plus 2 electrons. And because I flipped it now, it becomes positive 0.762 volts. And when I add these together, just as I've done before, we can see the electron and the electron cancels. I'll have my total balanced reaction, copper 2 plus zinc metal makes zinc 2 plus copper metal. And then I would just add these together to get my 1.104 volts. So either way, I get the same answer, right? I get the same thing out of this. So that's our challenge, is to figure out how to arrange our two half reactions to maximize E cell to be a positive and maximum possible potential. That's our goal, okay? So more examples coming, and I'll record those in a part B video.